Last time we looked at capacitors, what they do, and the displacement current going through them. Also what happens if you put reverse voltage on a polarized cap. Don't do that. So we know that the charge on the plates of the capacitor is equal to the capacitance times the voltage applied, and the current or displacement current for the capacitor is equal to the time derivative of that charge, which is equal to the capacitance times the time derivative of the voltage applied. So we say that the voltage over the capacitor does not change instantaneously, and here's the reason for that. So if we have over a time interval of 0 to t1, that the voltage is equal to alpha times t, where alpha is your slope of this line right here. If we take the time derivative of that, we see that the current is equal to the capacitance times that slope. Now if we increase alpha, we increase the slope, and if we increase alpha to infinity, we essentially have a step function where we jump up instantaneously. What happens then is that the time derivative of that would give you the capacitance times infinity, so we would have infinite current at some extremely small time, but we don't see that in reality because infinities don't like to exist in electronics. So that is why we say the voltage does not change instantaneously. Now what we can look at is how to actually analyze this circuit. So if we are just after t equals 0 and our switch is closed, we know that we will have some current, which is I, and we can make a Kvl loop for the circuit and say that voltage minus the voltage of the resistor minus voltage of the capacitor is equal to 0. We know what our voltage over the resistor is, so we have I times R, and we know what the voltage over the capacitor is based off of this equation, which is Q over C, and that's equal to 0. Now we know that because we have a series circuit here, the displacement current for the capacitor is going to be the same value as the current going through the resistor, which allows us to say that V, which is the source voltage, minus R times dq dt minus Q over C is equal to 0. We can rearrange this as dq over dt plus Q over RC is equal to V over R. And what we have here is a non-homogeneous differential equation. And from that, we know that Q of t will take the shape of the homogeneous solution plus the particular solution. And for our homogeneous solution, what we do is we set this to 0, and we have dq dt plus Q over RC equals 0, and this yields the solution that Q homogeneous of t is equal to Q naught e to the minus t over RC, where we don't know what Q naught is, but we will get there. So for the particular solution, we look at this V over R, and we see that that's a constant, so we will use the method of undetermined coefficients to say that we will estimate the particular solution to be a constant. From this, the derivative of the particular solution is equal to 0, and that allows us to say that plugging back into this equation right here, that we have A over RC is equal to V over R, or A is equal to C times V. So now we can solve for the total solution and say that Q of t is equal to Q naught e to the minus t over RC plus CV. We can divide by C, and we see from up here that Q divided by C is just going to be the voltage over the capacitance. So we say VC of t is equal to Q naught over C e to the minus t over RC plus V. but we don't know what Q naught is, so we can start to look at initial conditions. Now, if we have an uncharged capacitor, which we do because our switch was just opened and we know that the voltage does not change instantaneously, we know that the voltage at time equals 0 should be the voltage at time equals just past 0. So we can take a multimeter and measure the voltage of an uncharged cap, and we get that that's equal to 0. So what we can say is that the voltage over the capacitor at time equals 0, which would be equal to Q naught over C plus V is equal to 0. And this yields that Q naught is equal to minus V over C. Now plugging this in, we see that Q of T over C, which is equal to V C over T, which is the voltage over the capacitor, is equal to minus VE to the minus T over RC plus V. We can simplify that to be V times 1 minus E to the minus T over RC. And that's going to be our voltage over the capacitor. So now using Ohm's law, we can see what the current is, and we know that the current over the resistor is going to be the same as the displacement current for the capacitor. So we can use Ohm's law to say that V minus Vc of t over R is equal to the current going through the resistor, and that is equal to current, displacement current of the capacitor. And we can easily just do that subtraction, and we see that IC of t is equal to V over R, e to the minus t over RC. So now we know our current and our voltage for our capacitor. We can then look at something called the time constant, which is the RC time constant, also known as tau, which is simply equal to R times C. This allows us to write the voltage over the capacitor as V times 1 minus E to the minus T over tau, and our current as V over R, E to the minus T over tau. And we can plot these. So we have voltage against time, then current against time. We can see that our equation for the voltage starts at 0, and as time goes to infinity, we reach the final voltage of the source applied to it. After 1 time constant, or 1 tau, we are at 63% of that voltage. And for the current, the displacement current through the capacitor, at 1 time constant, we are 37% of the initial current from time equals 0. So as we get to a higher voltage, our current decreases. Next time, we can look at the following circuit, where we will have the same thing, except now we are adding this node here. So at t equals 0, the switch closes to here, and we will have our voltage source in series with the resistor and the capacitor, so we would expect the same kind of charging. But then after 10 time constants, we are going to put our switch to this pin, which allows our capacitor to discharge. So we'll see how the capacitor charges up and then how it discharges